Hi, today in this video I will go through the solution of exercises sheet for chapter 4 on the vibration rotation of diatomic molecules. You are given these constants that usually you will be also given in the exam. So let's start with exercise 1 that says that the vibration, rotation, or rotation vibration spectrum of carbon oxide has in the near infrared an intense band in the region between 2100 and 2200 centimeters minus 1. With a low resolution device, we obtain the following lines. So you are given actually the line series obtained for absorption. Well, it's not written absorption, but basically we work in absorption by default unless it says differently. Now the first question in this exercise: determine the inertia moment or the moment of inertia, the internuclear distance, and the vibration frequency of the CO molecule. And then we need to determine the value of the centrifugal distortion constant of the same molecule. So how are we going to think about the problem? As I said to you in the course, what we can do basically is when we have experimental data, we can derive from that values due to the spacings and the expressions of each spectral line. So first of all, let's draw, if you want, the situation. Basically, we can notice very easily that these spectral lines, if you just draw them, not on scale, but with numbers, and you calculate the difference between them, you notice that the spacings are constant, equal to 4, and there is this middle gap which is basically equal to 8. So this is characteristic of the vibration rotation spectrum with the two branches, the rich branch and the poor branch, R and P branch, sorry. This is something you know from the course. Now from this we need to extract information that would allow us to derive the moment of inertia. So the moment of inertia is I, which is mu r squared, but we don't have r, so we need to find it also. So the moment of inertia should come from somewhere else, and the only other place that we know where we can get the moment of inertia I is the value of B. And yes, we can get B from the spectrum. So let's see that. Since the central gap is almost the double of the spacing, so we can assume that we are easily considered in the model of rigid rotator, vibrating rigid rotator, and especially in the case where there is no interaction, because B is constant and it's not changing between the rich band and the poor band. So this is the first approximation that you have seen in the course, and based on this approximation, well, the vibration transition leads to this delta G between G corresponding to V equal 1 and G to V equal 0. And this is given by omega E equal minus 2 omega X, which is equal to omega 0. And then the rotational transitions obey the selection rule, delta J equal plus and minus 1. So for the rich band, you know that delta J must be equal plus 1. So the rotational spectral term, delta F, is given as 2bj plus 1. So this is something you must know. This is not going to be given in the exam. But you must know that this is the difference for the R branch, and that the R branch starts, these transitions, they start from the value of j equals 0. So that's the first line in the rich band. For the poor band, delta J minus 1, so it's Fj minus 1 to Fj, or Fj to Fj minus 1 in absorption, which is equal to minus 2bj. And you must also know that the first line, the first transition that could happen for the P branch starts from j equal 1 and goes to j prime, or the second level of vibration, j prime equals 0, as you have seen in the course. And These also things you should also know, huh? That the spectral value, so that each line on the spectrum, so the wave number or nu bar spec that I've defined several times, is given for the poor band in function of j as this value, and for the rich band as a function of j in this expression. Obviously here I repeat that the r starts from j equals 0, so the first possible transition starts from j equals 0, while for p the first possible transition starts from j equal 1. Now if I draw it again, now we can easily see that the difference in between two consecutive rich or lines on the rich branch is equal to 2b. Same thing for the poor branch, and this you can just get by taking j plus 1. So you make nu bar p j plus 1 minus nu bar p j, or something like that. It's the same thing for r, so you make the difference and it's 2b. While the difference between the first line in the poor band and the first line in the rich band, the difference in between is 4b. Now remember this remark. If you are asked to give names of these lines, okay, usually we call them R1, R2, R3, right, which is the J, while here we call it P1, P2, okay, etc., etc. Or you can say I want to call it R0 and then R1, and in this case you would have called that based on the J number. It's the same. The important part is this is the name. If you want, if you are asked to give the name, this is the name of the line. This is how we call it. Okay, great. So we've taken this note. So since we have 2b or 4b and we have these numbers, so we know them, it's given. Look, they are here. So this is 2b now. Then we can extract b. In centimeter minus 1, it's 2 centimeters minus 1. Now we have b. So remember why we were looking for b. We were looking for b because we needed to actually get I. And this expression you must also know. You're not going to be given this expression. So b equal h over 8 pi square ci. So we solve for I, but we have to make to pay attention to the fact that c is in meters per second. So p has to be in meters minus 1. Okay, b, sorry, has to be in meters minus 1. So we transform it from centimeter minus 1 to meter minus 1. Then you put all the values in here and then you get your I, which should be, as we've calculated it in the other chapters, usually with the order of minus 46, minus 47 kilograms meter square. Okay, he needs R also. The question is asking to find R, the internuclear distance. Well, I equal mu R squared, so R is the radical of I over mu. We have just got I, we need mu. Or it's a CO molecule, so mu CO is mu C, you know, it's the reduced mass. We don't forget the Avogadro number. And transform it to kilograms, because usually this is in grams. And then we get this is the mass. Why we transform it to kilograms? Because we need to fit it in here afterwards. And this should be I is in kilogram meter square. So this should be in kilograms too. So the radical of meter squares gives the radius, or the distance in meters. Okay, so if you calculate R then we have R almost equal to 0.11 nanometers. It's very small. Now, let's go back to the questions. Well, second question asks for determining the value of the centrifugal distortion constant of the same molecule. So we need to determine D. Now remember that D is much smaller than B. Okay? And D just appears when we talk about centrifugal distortion. So when the... Sorry, is there a question before? Well, it seems that... Okay, sorry. We have to determine the vibration frequency of the CO molecule. Okay. So we have determined the nu E. Okay? So if we need to determine a nu E, which is the frequency of vibration, we need to know omega 0. It's the pulsation. Why? Because we're going to use this omega 0 to determine the energy or the frequency. So to get omega 0, you have to remember that any of the spectral lines, you know their expressions. It's omega 0 plus 2b for the first line and omega 0 minus 2b. So that's the first line in the rich band. Okay, so that's first, let me write it down, first line in the rich band in R. Or you could have used the first line in the P band. It's the same. It's going to be omega 0 minus 2b in that case. So you make the calculation and you get omega 0. So omega 0 is nothing else than, I mean, omega E basically. It's the same. Yeah. So the frequency is nu is C nu bar. Why? Because nu bar is nu over C. It's the wave number. So since we have the wave number which correspond to this middle transition that is not allowed, it's equal to C omega E, which because omega E is this wave number. And then from that we calculate the frequency, which is around 6.4 10 to the power 13 Hertz. Last question, determine D. Determine the centrifugal distortion constant. Well, the thing is, since the spacing between the spectral lines is totally symmetric or symmetrical, this suggests that we do not have enough spectral resolution to distinguish the small difference resulting from the presence of a distortion correction. Because you've got to remember that distortion correction, first of all, shows up at high energies, and second, it's extremely small, and it would create a very small variation between the distances. So since we have a resolution that is giving us values totally symmetrical, it means our tool that we are using in this exercise cannot tell us experimentally what is the value of D. And that's the answer. For the second exercise, the rotation vibration spectrum of hydrogen chloride, you are given the masses, so notice that. Okay, so you are given the masses in here. Has in the near infrared an intense band, so this is the band, right? In the region between 1900 and 2300 centimeters minus 1. With a spectrograph presenting a high resolution, so we really have a very good resolution, 0.01 centimeters minus 1, we observe the following absorption lines. Okay, great. So obviously you should immediately know now that, well, this is the rich band and this is the poor band. Okay, great. Now, you are given in this exercise the values of the wave numbers for the lines on the rich branch and the ones for the poor branch. The question says, from the wave number of the branches P and R of this band 1, 0, what does mean 1, 0? It means that we are going in the vibration. This means, so we are going from V equals 0 to V equal 1 on the vibrational levels. Okay, so that's this band seen here correspond to the transition from V equals 0 to V equal 1, and these lines correspond to all the possible transitions of the rotational states in this jump of vibrational energies. So the question is, calculate the values of the rotation constant V0, so corresponding to V equals 0, V1 corresponding to V equal 1, and V equilibrium, and then deduce the internuclear distance Re at the equilibrium. So let's take them part by part. First of all, since it says that there is a V0 and there's V1, then V is not constant. Okay, when does that happen? Well, that happens, before I do that, the spectrum corresponds to this. So since we have to determine the BV for 0 and BV1, this suggests that we are, in this problem, considering the model of the real rotator with an interaction between vibration and rotation. Okay, so it's not said in the exercise, so we're writing it here. D is supposed negligible. Okay, so now what is the first thing I need to do? Well, you have to remember that B's, so to find B for each level of vibration, these in the course they were called B prime and B second, if you remember that in the video for the lecture. Well, to determine the value of B's, there's only one method that we use, at least in this course. We have to look into all the transitions that have the same final level and all the transitions that have the same starting level. And these things would allow us to determine, for one case, the value of the B corresponding to the lower level of energy of vibration. So B0 would be determined if we take two transitions of rotation having the same final state, and B1 would be determined if we take two transition lines, difference in between them, that correspond to the same initial state. Okay, so what we are going to do first is we are going to draw these lines on a graph. So always draw because it's visual and you can see it. Now you will notice that for the rich band, so this is the rich branch. For the rich branch, the first starting line goes from J equals 0 to J equal 1. That's known. And then the following will be 1 to 2, etc., etc. And here, in the poor branch, we start from J equal 1 to J equal 0. And then the second one would be from J equal 2 to J equal 1. Now, if I ask you to draw them, you would basically draw something like this. You would say that, okay, I have the energies here. This is V equal 0. Okay, J equals 0. And this is, perhaps I must do this in a bolder line. So this is V equals 0, J equals 0. And this is V equal 1, J prime equal 1, equals 0, sorry. J prime equals 0. Okay? And then you draw the smaller lines in between. So now you have J equal 1, J equal 2, J equal 3, J equal 4, and then here you have J prime equal 1, J prime equal 2, J prime equal 3, and J prime equal 4. So that's 1, 2, sorry, let me draw them in blue. So that's going to be 1, 2, 3, and 4 for J. So that's J. And this is for J prime. It's going to be 1, 2, 3, 4 again for J prime. And this is J prime. Okay, obviously you have the possible transitions. So we go from J equals 0 to J prime equal 1. This is the first one in the rich band. And then we go from 1 to 2, and then we go from 2 to 3, and then from 3 to 4. This would be the first four lines in the transitions for the rich band. So this is the R branch. However, for the other one, well, we start from j equal 1 to j equal 0, and then from j2 to j1, and then from j3 to j2, and then from j4 to j3. And this is the four first lines, if you want, in the P band branch. Okay? Now you have got to notice then that if you want to see, so you take these two levels, for example, they have the same final state. Okay, same final state, same final. So if you take the difference in between them, then the difference will be just coming from here. Okay? And it will give you, because here we have B0, and for these lines we have B1. So if you make the difference of two lines having the same final state, the difference will be related to B0, and the inverse too. If you take two lines that start the same initial, so like these two, if you take them, they have the same initial state, and then their difference, or the difference in between them, will just be depending on B1. Okay? Great. So, yeah. What we've got to do is to know that the spectral lines, and probably this you will be given if it's needed, that the spectral line for the poor branch is given with this relation when B is not the same for the two vibrational levels. So when there's B0 and B1, well, this looks like this, and the same thing for the rich band. So since we need to determine B0 and B1, we proceed with the method of differences that I just said. So let's pick up these two lines. Since we have their values, so you can just notice them from the graph that you drawn. So these two lines that have these energies, well, have the same final state. You look, this is same final state. So if you take the difference between them, then the difference between them is 4B0, because the final state is B1, then the difference in between these two lines in the rich and poor branches that ends up with the same final, it's immediately related to B0. Okay, and since it's the common, so this is with J equal 1. Why J equal 1? Because you take the value that is common for the two states, in this case J equal 1, the final one. Then you implement the difference. Delta F is this difference that comes from the values that you have here and here. Okay, you put J equal 1 and it turns out to be 6B, and then you can find B0. You do the same thing for B1, but in that case you actually use the two lines that start at the same initial value. So they start at the same initial value. Just pick them out from your drawing. So that's same initial, and the same initial values, their differences will be just related to the second B, so B2, J plus 1. And also the J that you need to take is the one that is common, which is here equal 1. You put this difference equal to 6B2 and you get B2 as you've got B0. Now you have B0 and B2, that's the first part of the question. But the thing is, well, you have got a lot of lines. Look, there are a lot of lines that actually could be of the same final and initial state. So what should I do then? Which ones should I take to get B0 and B1 or B2? Well, the method that we do is you actually go through all the lines that have the same higher level. If you want, so here we are going to determine B0 average value from all the spectrum, average value. Why? Because if you look into the lines, then you can grab that there are a lot in between these two branches that end up with the same level. So the ones that end up with the same level j equal 1, you make the difference in between them, you identify them from the graph, and this is the value. Now this difference corresponds to j, well, I mean the common j is 1 because that's the final state. So j plus 1 is equal to this value. Now what we do in here is we are just dividing this by j plus 1. If you ask why, it's just simply because if you go back, look, the difference is 4b0 j plus 1. So if you divide the difference by j plus 1, you will get to 4b0. And that's what we're doing. You take the difference for two lines, one in the rich and one in the poor, that end up with the same final value, which is 1 in this case. So your j is equal to 1. Your difference is given from the values of the experimental data. You divide them and you get 4b0. So these values are the ones for 4b0 for all the lines in the rich and poor bands that end up with same values. Either it's 1 or 2 or 3 or 4. So you take all these with the available data that you have, and we have got different values for 4b0. So what we do is we just take the average of this. So we make the mean value of all this. So you add them and then divide them by the number, which is 10. And then this gives you the average value of 4b0. You divide by 4 and then you get b0 as a average value. Obviously it's close to the one that we have gotten here, but that's an average value, so it's close, not the same. And you do the same thing for b2, but for b2 you have to notice something, that you take all transitions that start from the same line. All transitions with a common starting level, with a common or same starting level, or same start level, okay? And then you follow the same thing. So for all couple of R and P branches, spectral lines that have the same initial value of energy, you take the difference in between them. It's also equal to 4b1 in this case, or b2, sorry, 4b2 j plus half. So you take the difference, you divide by j plus half, taking j as the common value for the same start level, and then you get to 4b2. You take the average value, and then you have the average value of 4b2. You divide by 4, you have the average value of b2 from all this experimental data of the band. Now we need to determine BE. So we have determined B2. This is B0 here, okay? It's just the name. We need to determine BE. Well, you should remember that there is a relation that is given at the last part of the chapter in the course, that B is a function of V, for a given V, is BE minus alpha E V plus half. Okay? What is alpha E? Alpha E is the difference between two consecutive values of B's. So that's the B for two levels of vibration that are different the one from the other. And in this case you have B2 and B0, so we have B0 and B2, so that's 0, it's not 1. And you take the value of them, the difference, and then you have alpha E. So here we have alpha E. We need BE, so we need to choose a BV value that we use its value corresponding of V. So let's choose B0. So B0 is BE minus alpha E that we've just got, V plus half, or V, if we've taken B0, is 0. And then from that we can calculate BE, since we know B0, we've just calculated before, and we have calculated alpha. So we find BE is equal to this value. Now BE is the equilibrium, right? So from that we can get the intermolecular distance, and we can get a lot of other things. So we need to remember that this expression you need to know. We can't get into E before going through I and then mu. So we solve for I, taking into consideration that we have to change this into centimeter minus 1 to change it to meter minus 1. And then we get I by doing this calculation. You just put the values, but notice this should be in meters. I'll write it big, -1. Don't forget. Okay, great. Now we have I, or I equal mu r squared, and r equal radical I over mu. So we need to calculate mu. You are given in the exercise the values on the name of the molecule, 2 and 35. So this is what you do. You do the reduced mass, you divide by number of Avogadro, and then you don't forget to transform it to kilograms, because these values are in grams per mole. And then we get mu, we put it in this expression, and then we get into the value of R by using this expression. For the question B, let's go back to the question slide. In B, it asks us to determine the zero gap, the bend center, the vibration rotation alpha interaction constant. I mean, this we actually did before. So it's a misplacement of the question, but that's not a problem. Now, what is the zero gap? And what is the bend center? What does that mean? Okay. Well, perhaps you know, perhaps not. So if you don't, this is the zero gap. Zero gap. Okay. And the center is this forbidden one. This is the center. Omega 0. Okay. Great. So how we can determine that? Well, you know, the gap is the difference between the spectral line corresponding to the first transition in the rich branch minus the spectral wave number line for the first transition in the poor branch. You have these values, just to calculate them, it's a gift result. Now, how to determine omega 0? Now, to determine omega 0, you have to remember the expression of a line, or in general, or if you want the first line in the poor branch or the first line in the rich branch. Well, it's either omega 0 minus 2b0 or omega 0 plus 2b1, depending which one you choose, because b0 and b1 are not the same. If they were the same, this would have been 2b and plus 2b, and the difference between them would have been 4b. This is not the case, obviously. So we have calculated b0, and you have these values. So from this you can calculate omega 0, or from this omega 0. So it's sensibly the same values. And this is how we get the omega 0. Now, another important question. It says the center of the bend to 0 now. Now notice, look here. When I said 1, 0, it means from v equals 0 to v equal 1. Now, bend to 0 means that we are going from v equals 0 to v equal 2, which is in the vibrational state. This is not a fundamental transition. So it happens, it's allowed, but not with the highest probability. But now it's the problem, or the question is saying that it happens. And it happens at the center of it is at this value of the wave number. So determine omega E for this band, and by using this value, the force constant. So we need to determine omega E for the second band, or the band from v equals 0 to v equal 2. So immediately, if this happens, or you get asked about this, you have to remember that once we talk about the harmonics, so the transitions that are not fundamental from v equals 0 to v equal 1, we have to use the fundamental one and the harmonic and figure out the values from a relation between them. That's always like that. So how we do this? Okay, so we recall that when delta v equal plus minus 1 and delta v equal plus minus 2, we identify the fundamental spectral line of vibration transition and the harmonics. So sorry for it's not very focused, but it's fine. For the fundamental transition in absorption, new one, which is the central line that we just calculated, if you want, new, it's the middle of the gap, is this value. And the middle of the gap for the second transition, so from v equals 0 to v equal 2, it's given to us, just given in the question. Now what we have to remember is these relations. These relations for the spectral line of the fundamental transition, fundamental in terms of vibration obviously, and here is the first harmonic. So to remember that, you just go to chapter 3 and look at it. First harmonic. Okay, so what I did is I just multiplied the first line by 3, and then I did the difference between them to exclude omega e xe, because I don't know xe, and then I get that this difference is equal to omega e. Then I have omega 1 and omega 2, I have them. I just got omega e from this, and then if I put back omega e in either of the two equations, I will get to omega e xe. Remember that when we have the harmonics. Okay? Great. So do we have other questions? Yes. From that, he said, from that determine K. So K is the spring constant of the bond. Well, basically, this nu E that we just determined, or omega E that we determined, we can extract the frequency of the transition that would have happened at this value of omega E, because at omega E, remember, the transition does not happen in the rod vibration spectrum, because the corresponding vibration transition would not obey delta J equal plus minus 1. But we can still calculate the values even if they don't show up, because we know the physics behind. So we calculate omega E corresponding to the value, nu E, the frequency corresponding to the value of omega E we just determined. But nu E is nothing else than 1 over 2 pi radical k over mu. Okay? Now for the intelligent ones, if you want, you could just say, well, look, this is nothing else than omega E over 2 pi. Because don't be so intelligent, Professor. We know that omega equal 2 pi f. We know that. So we could have used just omega E, which is correct. If you're not asked to determine nu E, you don't need to determine it. Now, radical k over mu, you calculate for it, and then k is the value of omega E that you calculated times mu, and so you just calculate mu. Or I think we've calculated it before, and then you get k. Obviously, you have to take care of the units. Mu should be in kilograms. Okay, and this is in hertz. And then your K would be in then also in international system Newton per meter. Okay. Now we get into the final problem in this exercise sheet. It's on the spectra or spectrum of rho vibration, so rotation vibration, for the CO molecule. Well, this is a text, you can read it, I will not read it now, but well, we have here the band for CO, okay, within a certain span of wave numbers. Again, I would like to remind you that these are called names of the peaks. Okay, names of peaks. So don't forget that. And we name the peaks based on J values. So the first rich line, or the first line in the rich band, this actually goes from 0 to 1, so we call it R0, while the first line in the poor band goes from 1 to 0, because delta J minus 1, so P1, etc., etc. Okay. Okay, so the first question, the first absorption line of the carbon monoxide rotation spectrum C12 016 was observed at 3.8 centimeter minus 1. Calculate the rotation spectroscopy constant B, its inertia moment, and its internuclear distance. Now, look, 3.8 centimeter minus 1 cannot be the value for a line. It cannot, obviously, because each line is in the 2000 something. So when we say it like that, it suggests, it means that that's how far it is from the central gap. So this 3.8 is from here to here. Okay? Great. So the first observable line would suggest that delta J equal +1. I can appreciate that for some of you we might ask, how would we know that that's delta J +1? Well, I mean, we will tell you in the exam, we won't make it that not obvious. But what's interesting is you have to be careful that just don't take things as they are. Think about the numbers. This number cannot be the value of the spectral line. It's how far this line is from the middle of the gap. Which means that this is the, if delta J +1, so this would be that this is the spectral line, the spectral wave number of the first line for the rich band, which is positioned at ω0 + 2b, right? So if it's far from the center by this value, and the center is at ω0, then 2b is equal to this value. So, okay, so 2b is this value, so we get b. Now, since we've got b, we need I. So this, we should remember it, you know it. You transform b into meters -1, you put it in here, and you get your I. Okay, don't forget that. Now, internuclear distance, I equal μr². Usual thing, you have everything for C12 or 16. You put it, don't forget the Avogadro number, and don't forget to transform it to kilograms, because the numbers are in kilogram per mole, and then you get R around 1.13 angstrom. Now, it's so easy, it has been redundant so far. Second question is a slightly different one, and here I need you to focus on this. We actually said that in the slides of the lecture, that when we have isotopes, because now we start talking about this absorption line for C13 016, so that's an isotope for the carbon C12. So when we have isotopes, immediately think about ratios of B's, which will be equal to inverse ratios of mu's. Okay, don't forget that. In your brain, the method should be clear. When we have isotopes, we should think about ratios. Okay, so let's see how we are analyzing it. So the first line is at this value. Obviously, it's the same idea. So 2b equal to this value. We get b. We put it in I, we get I. However, if you want to calculate the atomic weight of C13, so we need to find mu. But to find mu, and we have I, we need R for the C13O. We don't have it, and we can't calculate it because we suppose that we don't know mu for C13. So what we do is, as I said, you have to remember that B is a function of 1 over mu. So if you take Bi over B, it's mu over mu I. So you inverse the ratio of mu's for a given ratio of B's. Now, what are these B's? B for C13 that we've just determined over B for C12 is the mu for C12 over mu of C13. And this way, you just calculate mu of C13. Okay? We just found mu of C13. Okay, so you just forgot about this because here I was doing calculations. I must have not put this. Okay, so again, the message in here, isotopes, I should think about ratios of B, which will be give me a ratio inverse of mu's. Great. So we have determined what we want in this question. The second one is the spectrum showed at the beginning is centered at this value. So that's omega 0. Calculate this force constant. So it's giving omega 0. So again, omega 0, you transform it to meters, and you calculate the frequency from it. So C times omega 0, it gives you the frequency. Now the frequency, or 1 over 2 pi radical k over mu, same thing you should have said also. You can actually use it immediately from here by removing the 2 pi, it's the same. So you have everything, okay? The mu that you use here is basically the mu of the C12, okay? Because we are taking, look, mu is the C12, because the spectrum that you have seen is the one for C12, CO, C12, O16. This is just math, huh? You just put values and then you get the force constant. It's actually a huge force constant, 1854 Newton per meter. So you need that much newtons to actually move the C and O molecules, the one from the other, by 1 meter. So this newtons, 1854 newtons, correspond to a mass in kilogram, if we take G equal 10, to 18,540 kilograms. So you need 18 ton of mass to actually move the C and O away from each other by 1 meter. Obviously you need, basically if you move them by 1 meter you break the bond, but you need 18 ton of mass to do this. So imagine that you can grab the molecule from one side, so that's the O and that's the C, they are bonded together. Imagine you can grab it from here and you attach a mass to it. Well, this mass should be 18 tons, so that you can basically, around 18 tons, break the molecule. So it's strong. Well, question D, the force constant of two isotope molecules are similar. So it's telling us that the K for C13 and CO to C12O are the same. So now calculate the position of the middle position, the center of the C13O16. Well, same thing, but it's the inverse. Now he gave us the K for C13, and we have calculated the mu of C13. We just calculate the frequency then, and then we divide by pi. So we multiply by pi to 2 pi to get the omega E for C13, which is the center of the wave numbers. For question E in this exercise, I'm not going to solve it. You're not responsible for it. That's all. Thank you.